Out there, beyond the reach of human eyes, two silent pioneers are still screaming into the cosmic night. Pioneer 10 and Pioneer 11 launched over 50 years ago, hurtled past Jupiter and Saturn, then plunged headfirst into the interstellar void, carrying humanity's deepest dreams into the darkness. For decades, we tracked their every whisper, meticulously charting their impossible journey through the solar system's icy edge. But then, the data started to lie. Tiny, persistent, and utterly inexplicable, an invisible force began to drag them back. A phantom hand clutching at their heels, slowing them down just enough to break every single law of physics we thought we knew. What if, even at the very edge of our understanding, a cosmic ghost was pulling them, defying every truth we held sacred? These aren't just hunks of metal flying through space. They are our eyes, our ears, our daring little fingers reaching into the cosmic unknown. Pioneer 10, launched in '72, then Pioneer 11 in '73, became humanity's vanguard. They were designed to smash through the asteroid belt, brave Jupiter's crushing radiation, then slingshot past Saturn. And they did it. They sent back breathtaking images, ripped open our understanding of the gas giants, and then kept going. They punched through the heliopause, the solar wind's last gasp, and plunged into the true interstellar void, the first objects ever to escape our sun's magnetic bubble. But here's where the cosmic nightmare began. For decades, we listened. We tracked them with the relentless precision of the Deep Space Network, pinging them with radio signals, measuring their speed, their trajectory, their every micro-movement across billions of miles. We knew exactly how gravity should pull on them, how solar radiation should gently push. Our equations were solid, tested, proven. Then the whispers started. First, a tiny deviation, barely noticeable. Then it grew, a persistent, impossible drag. Both Pioneer 10 and 11, across vastly different paths and distances, were slowing down. Not much, just a hair's breadth. Picture this: you launch a perfectly calibrated car, expecting it to coast, but it's suddenly losing a fraction of a mile per hour, every single second, for no reason. This was no malfunction, no random glitch. This was a steady, constant, utterly alien force acting on them. The numbers screamed it: an anomalous acceleration of 8.74 x 10 to 10 meters per second squared, always pointed back towards the sun. To grasp that, imagine a feather floating in the vacuum of space, experiencing a force so tiny it would take days to move it a single centimeter. But this force was there, relentless, defiant, a cosmic whisper that became a thunderclap in the quiet halls of physics. It wasn't a sudden jolt, it was a constant, almost gentle, but utterly undeniable pull. A phantom hand reaching across 12 billion miles, tugging our trailblazers back. The universe was playing a cruel trick, and we had to find out why. The moment that anomalous deceleration screamed from the data, the alarm bells shattered the calm of mission control. This wasn't just a glitch, it was a cosmic challenge, a direct assault on our most fundamental understanding of gravity and motion. The scientific community launched a full-scale interrogation. Every single possible culprit, every mundane explanation was dragged into the spotlight, meticulously scrutinized, and ruthlessly eliminated. First, the obvious suspects: fuel leaks. Could a tiny, unnoticed trickle of propellant from the probe's thrusters be gently pushing them backward? Engineers tore through decades of telemetry, cross-referencing every thruster firing, every pressure gauge reading. Verdict? No. The thrust was precisely accounted for, too small, too erratic, or simply non-existent to explain the constant, uniform drag. We knew exactly how much fuel was left, and it wasn't enough to hide such a consistent force. The phantom tug persisted. Next, the sun. Solar radiation pressure. Light itself exerts a tiny push. Could the sun's photons be acting differently than predicted? Or perhaps the solar wind, the stream of charged particles blasting from our star? Scientists calculated, simulated, and recalculated. The probes were far beyond the heliopause, where the solar wind dwindles to an almost imperceptible breath. Its effect was orders of magnitude too small to account for the anomaly. The sun was innocent. What about the probes themselves? Could their instruments be malfunctioning? creating false readings. Teams meticulously cross-referenced the data from Pioneer 10 and 11 against other deep space missions like the Voyagers. The Voyagers, though similar, weren't showing the same consistent anomaly. This pointed away from a universal instrument flaw and back to something unique about the Pioneers. The probe's internal systems were cleared. Then came the thermal riddle. These probes were powered by radioisotope thermoelectric generators, RTGs, essentially nuclear batteries converting heat from decaying plutonium into electricity. They were mini onboard furnaces. Could the heat radiating off the spacecraft unevenly create a tiny propulsive force? Imagine a tiny invisible jet engine made of heat. This was a strong contender. But the RTGs were on booms, shielded, designed to radiate heat away. Initial calculations said no, not enough. The heat was largely symmetric. The anomaly still a defied explanation. We even considered the most outlandish yet still conventional possibilities. Could the probes have tangled with a cloud of dust? An invisible, ultra-diffuse gas? No. The emptiness of interstellar space is profound. Any such interaction would have been far too weak to create this consistent drag. Software errors? Every line of code was reviewed. Every algorithm checked. Nothing. This wasn't a computer dividing by zero. This was reality itself refusing to add up. The scientific world was on the brink. Every conventional explanation was meticulously torn apart, piece by excruciating piece, and found wanting. The anomaly wasn't going away. It was a cosmic cold case, stubbornly refusing to yield its secrets, pushing us closer to a terrifying conclusion. Our understanding of the universe, our very laws of physics, might be fundamentally incomplete. This wasn't just a puzzle. It was a crisis. If you're as gripped by these cosmic mysteries as I am, smash that like button and subscribe. We're just getting started on this journey to the edge of the unknown. With every conventional explanation brutally murdered by the data, the scientific community faced a terrifying precipice. When the known laws of physics fail, when every logical deduction hits a brick wall, you're left with only one choice: challenge the laws themselves. The Pioneer Anomaly wasn't just a bug. It was a cosmic scream for new physics, and the whispers of heresy began to grow into a chorus. The first, most audacious thought: what if gravity itself was wrong? Einstein's general relativity, the very bedrock of modern cosmology, had reigned supreme for a century. But what if, at these vast empty distances, in the weak gravitational fields far from our sun, gravity didn't behave exactly as predicted? Enter modified Newtonian dynamics, or MOND. This radical theory, usually invoked to explain the rotation of galaxies without dark matter, proposes that gravity's pull becomes stronger than expected at extremely low accelerations. The Pioneer Anomaly, with its tiny persistent drag, seemed to fit MOND's predictions uncannily well. It was a tantalizing, almost forbidden connection. Imagine rewriting the rulebook of the universe because two tiny probes whispered a secret from the void. But MOND had its own problems, its own struggles to explain everything else we observed. So, the search for other, even stranger culprits intensified. What about dark matter? This invisible, mysterious substance, believed to make up 27% of the universe, interacts only through gravity. Could a diffuse, unseen halo of dark matter surrounding our solar system be exerting a tiny extra tug on the Pioneers? It was a compelling idea, like trying to pinpoint a ghost by the ripples it leaves in a pond. But modeling such a precise, consistent effect from an amorphous dark matter cloud proved incredibly difficult. It was like trying to catch smoke with a fishing net. Then came the truly mind-bending concepts. What if we lived in a higher dimensional universe, and some of gravity's force was leaking away into those unseen dimensions? Imagine our universe as a thin, stretched membrane, a cosmic trampoline. If gravity could bleed off into the bulk, the extra dimensions, it might explain why it seems weaker to us at certain scales. The Pioneer Anomaly, with its inexplicable extra pull, could be a faint echo from a hidden dimension, a subtle tug from a realm we can't perceive. It was like trying to explain a ripple in your pond by suggesting there was an invisible sea monster in a different, hidden pond next door. Some even dared to question inertia itself. Could the very resistance to motion, the fundamental property of mass, change at these extreme distances and accelerations, a concept known as modified inertia, or quantized inertia, suggested that the vacuum of space, far from being empty, might exert a subtle push against accelerating objects, a kind of cosmic drag. It was a truly radical thought that the fabric of reality itself might be gently pushing back. The stakes were astronomical. If any of these new physics hypotheses proved truer, it would rip open our textbooks, rewrite our understanding of space, time, and gravity. It would mean the universe was far stranger, far more complex, and infinitely more challenging than even Einstein had dared to dream. The Pioneer Anomaly was no longer just a technical problem. It was a battleground for the very soul of physics, forcing brilliant minds to confront the terrifying possibility that everything they knew was wrong. If you're still here, still wrestling with these cosmic riddles, then you're one of us. Hit that like button, subscribe, and join our expedition into the unknown, because the universe has more secrets than we can ever imagine, and we're just scratching the surface. For years, the Pioneer Anomaly stood as a defiant middle finger to our understanding of the cosmos, a tiny, infuriating whisper from the void that threatened to unravel the very fabric of physics. But then, after decades of relentless detective work, the cosmic ghost was finally unmasked, and the solution, in a twist of delicious irony, was both frustratingly simple and profoundly complex. The culprit wasn't dark matter, or extra dimensions, or a breakdown of gravity itself. It was heat. The very heat radiating off the probe's own radioisotope, thermoelectric generators, their nuclear power sources. Remember those RTGs? Those mini onboard furnaces designed to generate electricity from the decay of plutonium. Initial calculations had dismissed them. They were largely symmetrical. Surely any heat they emitted would cancel out, right? Wrong. The devil, as always, was in the details. Scientists, led by a brilliant team at NASA's Jet Propulsion Laboratory, launched a forensic deep dive into every millimeter of the Pioneer spacecraft. They meticulously modeled the complex ways heat radiated from the RTGs, not just directly, but also reflected off the spacecraft's main antenna dish and other components. Imagine a tiny, invisible spotlight of heat. That spotlight, tiny as it was not perfectly symmetrical. Some of it bounced off the back of the antenna dish and off other parts of the spacecraft, creating a minuscule but constant stream of photons pushing forward. Think of it like this. Every photon carries a tiny bit of momentum. When these photons blast off the spacecraft, they act like miniature thrusters. The vast majority of heat just radiated harmlessly into space, but a tiny fraction, the equivalent of a few watts of power, was bouncing off the dish and other structures, creating a slight, persistent, and unaccounted for thrust in the direction away from the sun. This meant the probes were being pushed forward relative to their trajectory, which registered as a deceleration source when viewed from Earth, because the external forces we expected were pulling them back. It was like a tiny, invisible, perfectly calibrated rocket firing constantly, pushing them gently away from us. This subtle, anisotropic, meaning non-uniform thermal radiation, was the phantom hand. It was an effect so small, so nuanced, that it had eluded detection for decades, hidden in the overwhelming complexity of the spacecraft's design and the vast cold vacuum of space. The final painstaking analysis, published in 2012, showed that this thermal recoil force precisely matched the observed anomalous acceleration. The cosmic ghost was gone, or was it? Even with this seemingly definitive solution, some physicists still harbor lingering questions. The thermal model was incredibly complex, relying on assumptions about the degradation of the spacecraft's surfaces over decades in harsh space environments. It required a deep understanding of heat transfer in vacuum, a field not always perfectly simulated. Was every single component accounted for? Every thermal pathway? The sheer difficulty of proving this mundane explanation and the extreme precision required revealed a deeper truth. Even the simplest forces, when operating over cosmic scales and times, can hide profound complexities. The Pioneer Anomaly wasn't a breakthrough into new physics. Not directly, but it was a triumph of scientific rigor. It forced us to push our observational precision to the absolute limit, to interrogate every assumption, and to scour every last corner of our known physics before daring to invent new ones. It taught us that sometimes the most profound mysteries are solved not by shattering our existing frameworks, but by understanding them with an almost terrifying level of detail. It showed us that even within the mundane, the universe can hide secrets that challenge our deepest certainties for decades. The ghost was unmasked, but the hunt itself refined our instruments, sharpened our minds, and made us better cosmic detectives. The Pioneer Anomaly, that stubborn cosmic riddle, ultimately surrendered its secrets. It wasn't a portal to new dimensions or a challenge to Einstein. It was a testament to the brutal, beautiful precision required to decode the universe's secret language. This wasn't about a grand revolutionary discovery, but about the relentless, painstaking process of science itself. For decades, this tiny, persistent tug on two lonely spacecraft forced us to look harder, to question deeper, to scrutinize every assumption about the cosmos. It pushed our engineering models, our thermal physics, and our data analysis capabilities to their absolute limits. It showed us that even within the known laws, the universe can hide astonishing complexity, subtle forces at play that scream into the void, demanding our attention. The resolution of the anomaly was not a defeat for new physics, but a victory for scientific integrity. It solidified our confidence in general relativity and our understanding of fundamental forces, demonstrating the incredible resilience of our current physical models, even under extreme scrutiny. It proved that, before we tear down the foundations of reality, we must first exhaust every single possibility within the walls we've already built. But the legacy of the Pioneer Anomaly stretches far beyond a mere heat signature. It's a powerful reminder that the universe constantly challenges us. It throws down gauntlets, daring us to find the hidden patterns, to decipher the whispers from the dark. Every solved mystery, every unmasked cosmic ghost only reveals more layers of complexity, more questions we hadn't even conceived. It reminds us that our quest for knowledge is not a finite race to a finish line, but an infinite journey into an ever-expanding cosmos, a journey that continually refines our instruments, sharpens our minds, and expands the very boundaries of human understanding. The universe is a master of disguise, and the Pioneer Anomaly was just one of its brilliant, frustrating illusions, teaching us humility and precision in equal measure. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.